Stone is a stubborn witness. Long after wood rots, long after metal corrodes into dust or is melted down and reused, stone remains. It holds its shape, it keeps its scars, it preserves not only monuments and walls, but the subtle marks left by the tools that worked it. For archaeologists, stone is more than a building material. It is a historical record that does not require ink. Its surface can preserve information for tens of thousands of years, and sometimes far longer. And when those surfaces are examined closely, they do not always match the simplicity of the stories we tell about the distant past. Written history is comparatively young. Even in regions with early scripts, the record of what people chose to document covers only a fraction of the human timeline. Stone, by contrast, can preserve evidence from eras that left no text at all. A cut face on a granite block, a hole drilled into hard rock, a pattern of grooves repeated with unusual consistency. These details may be small, but they are physically real. They exist outside tradition and expectation. They can be measured. According to researchers who study ancient architecture and quarry sites, many tool marks fit well with known methods: pounding with stone hammers, pecking with harder rocks, chiseling softer stone with copper or bronze, and polishing with abrasive sands. Often, those explanations are sufficient. Human skill is frequently underestimated, and the patience of organized labor can achieve results that seem impossible to a single person. But there are also cases that demand a longer pause. There are marks that look unusually uniform. There are cuts that seem to stray to be the product of simple, unconstrained hand work repeated at scale. There are holes that appear deep, round, and consistent in ways that resemble controlled mechanical motion. A cautious idea follows from that observation. Could some ancient societies have developed more advanced mechanical techniques than we usually assume, leaving behind traces in stone that outlasted the tools themselves? This does not require impossible technology. It does not require fantasy. The aim is simply to read the evidence with the same discipline we would apply to any other material record, separating what is known from what is inferred, and what is inferred from what is merely suggested. One of the most discussed categories is the presence of perfectly round holes. Across multiple ancient sites, stone blocks and unfinished pieces show circular holes that look drilled rather than chipped. Some are shallow, some are deep, often striking in their uniformity. In softer stone, round holes are not surprising. A bow drill with abrasive slurry can bore into limestone, and a copper tube combined with wet sand can grind into the material. In such cases, the metal does not need to be harder than the stone because abrasive grains do the cutting. The tool mainly guides the abrasive. Over time, the abrasive wears away the stone. But hard stone changes the equation. Granite, basalt, diorite, and similar rocks do not yield easily. Yet there are drill holes in these materials that appear clean and regular, sometimes deep relative to their diameter. Some show smooth interior walls. Some maintain a consistent circular form without obvious wobble. If these marks are examined closely, the question is not whether humans could do this at all, but what kind of process would be the most efficient and plausible. Modern drilling produces recognizable signatures. A rotating bit held with consistent pressure tends to maintain roundness and alignment. The walls of the hole are evenly scraped, and the axis stays stable when guided by a rigid structure. In an ancient context, rotation could still be central. The key issue becomes control of rotation, control of pressure, and control of alignment over time. Some engineers point out that deep, uniform holes in hard stone would benefit from a stable way to apply force. Human arms can rotate a drill, but fatigue and inconsistency become limits, especially as depth increases. A bow drill can spin quickly, but maintaining steady pressure while keeping the drill perfectly vertical grows harder with time. A weighted drill changes the dynamics. If a drill shaft is loaded with a heavy weight, gravity provides constant downward force. The operator's main job becomes keeping the tool rotating and aligned. This is not modern technology. It is basic mechanics, using mass and stability to reduce human variability. Even so, important questions remain. How were drilling edges shaped so they remained effective against abrasive wear? How was abrasive delivered and refreshed? How was the drill stabilized so the hole did not drift or flare? As the hole becomes deeper and more uniform, a simple handheld method becomes less likely, and a fixed drilling rig becomes more likely. A rig does not have to be made of metal. It could be wood, it could be stone. The important point is that it constrains motion. From holes, the evidence expands to straight cuts and smooth surfaces. Many ancient structures display stone blocks fitted with remarkable precision. There are long, flat faces that meet with minimal gaps. There are edges that run straight for meters. There are surfaces that appear planed down to a consistent level. None of this automatically implies advanced machinery. Skilled stonemasons can produce flat surfaces by pecking, scraping, chiseling, and then rubbing with abrasives until high points wear down. With enough time, a surface can become very smooth, but skill matters. One finely finished block could be the result of extraordinary effort. Hundreds or thousands of similarly finished blocks raise questions about process, speed, and repeatability. If a culture produced large volumes of accurately shaped stone, then either timelines were immense and labor forces vast, or methods existed that improved consistency and efficiency. It is difficult to explain using simple tools alone when a cut appears not only straight, but consistently straight across many blocks of hard stone, especially if the cut marks suggest a continuous motion rather than incremental chipping. Modern saws typically leave parallel striations, sometimes with irregularity connected to tool movement and vibration. Ancient sawing methods using metal blades and abrasive sand can also leave striations. The deeper issue is force and stability. A long, straight cut through hard stone requires the cutting line to be maintained over distance. Any wobble becomes visible, any change in angle produces unevenness that must later be corrected. According to researchers who have documented quarry marks, some ancient cuts look long and uninterrupted, as though the tool advanced steadily and did not constantly reset. In some cases, surfaces appear not merely separated but surfaced, as though the stone was deliberately brought to a plane. Surfacing is not the same as cutting. It implies controlled removal of small amounts of material over an area. In stone, that usually means abrasion. Abrasion can be slow, but it can also be systematic, especially when combined with reliable measurement. Some engineers argue that the most telling feature is not smoothness by itself, because smoothness can be achieved through patient polishing. The stronger clue is uniform flatness across a broad area, particularly in very hard stone. Flatness implies measurement and feedback. It suggests a process refined enough to produce similar results repeatedly, not once. Another theme emerges in repeated mechanical patterns, grooves, parallel lines, and identical markings that appear on different stones and across different areas of a site. Repetition can come from skilled hands, but mechanical repetition has a distinctive character. It tends to preserve spacing. It tends to maintain depth and angle. It suggests a controlled path that a tool follows. If these marks are examined closely, and if they are truly repetitive rather than merely similar, then the implication is not necessarily high technology, but constrained motion. Constrained motion can come from guides, frames, and templates. It can come from a tool that is forced to move along a fixed track. It can come from rotation that produces consistent arcs. It can come from a reciprocating action stabilized by a structure. In modern terms, we call these machines, but the concept of a machine is simple, a device that channels force in a predictable way. A lever is a machine, a pulley is a machine. A wooden frame that holds a drill vertical is a machine. Between primitive and mechanical is a wide middle ground. This is where an engineering perspective becomes useful. Engineers think in terms of torque, pressure, vibration, and rotational movement. Torque is the twisting force that turns a drill or drives a saw. Pressure is the force that pushes an edge or abrasive into stone. Vibration can create unwanted chatter, leaving irregular marks, or it can help abrasives bite if controlled. Rotational motion is especially relevant to circular holes and spiral striations. Some engineers point out that drilling hard stone efficiently requires sustained pressure and reliable rotation. If rotation is too weak, abrasive grains do not cut effectively. If pressure fluctuates, cutting becomes uneven and the hole can drift. If the tool vibrates excessively, the interior can become irregular. Modern drilling manages these variables using rigid materials and precisely shaped bits, but the same principles can be managed in simpler ways through mass, stable frames, and consistent abrasive technology. So what kind of tools would logically be required to produce these traces? A straight, uniform cut could suggest a saw guided by a frame, perhaps using an abrasive slurry. Deep, round holes could suggest a tubular drill with added weight, rotated by human power and kept vertical by a guide. Repeated parallel grooves could suggest a template, a jig, or a constrained tool path that keeps motion consistent. These are not impossible devices, they are solutions built from common materials, shaped by experience, and refined for reliability. Traditional explanations must still be treated seriously. Archaeologists have long proposed that copper tools, combined with sand and water, could cut and drill stone. In these methods, the abrasive, not the copper, does the cutting. This idea is well supported and aligns with known practices. Experiments have shown that with enough time, abrasive drilling can produce holes in hard stone. Similarly, sawing with metal blades and hard sand can separate granite slowly by grinding rather than slicing. But these explanations also face practical limits. Copper is soft and wears quickly. Keeping tools functional would require constant reshaping and replacement. Large-scale stone processing would demand steady supplies of abrasive, water, and labor, along with workshops capable of maintaining tools and managing materials. None of this is impossible, but it changes what we should expect. If abrasive methods were used at massive scale, then the system behind them becomes part of the story: logistics, training, standardization, and specialization. It is difficult to explain using simple tools alone when the marks suggest not only that something could be achieved, but that it could be achieved consistently and efficiently. This shifts the question from "could it be done?" to "how was it done in practice, at this scale, within the social and economic realities of the time?" A society can spend decades on a single monumental project, but if similar traces appear repeatedly across many sites, then we must also explain the production method that made those results repeatable. These traces matter because tools imply knowledge. If advanced methods existed, they imply more than strong arms. They imply planning, measurement, and specialization. Knowledge implies trained craftspeople. It implies toolmakers who understood wear and abrasives. It implies surveyors who could maintain straightness and level over distance. It implies organized systems for quarrying, transporting, and finishing stone. At the same time, caution is essential. Human perception is prone to projection. We recognize modern patterns because we live among modern tools. A straight line looks like a saw cut because we know saws. A round hole looks like a drilled hole because we know drills. Sometimes the simplest explanation is correct. Careful handwork can resemble machine work, especially after weathering softens roughness and erases finer traces. This is why careful study relies on measurement and comparison. Researchers document tool marks with close photography and scans. They examine striations under magnification. They compare ancient traces to experimental marks made using reconstructed techniques. They study the geometry of holes, the direction of scratches, the distribution of abrasive patterns, and the microscopic fractures in the stone. In these details, the stone becomes evidence rather than impression. Some engineers suggest focusing on signatures that are difficult to produce by unconstrained hand motion alone. Consistent spiral striations in a hole can indicate sustained rotation under stable pressure. Uniform diameter over long depth can suggest guidance. Parallel grooves with consistent spacing can suggest a controlled tool path. But even these clues must be handled carefully because simple tools can be improved by guides, and skilled operators can create impressive regularity. The safest conclusion may be that ancient stoneworking was not limited to the simplest picture of handheld tools. Between basic hand labor and modern industry lies a wide spectrum of mechanical methods, rigs powered by people, stabilized by frames, weighted by stones, optimized by experience, and made repeatable by measurement. This brings us to a practical question. Where did the machines go? Stone endures, but machines decay. Wood breaks down, rope rots. Metals rust, fracture, and disappear into recycling. Even in relatively recent history, tools vanish because useful metal is almost never left to waste. Over centuries and millennia, the material culture of machinery can be erased while the stone, too heavy to move and too stubborn to dissolve, remains. There is also the fragility of knowledge. A technique can be invented, refined, and mastered, and still be lost if the social conditions that support it collapse. Specialized knowledge depends on specialists. It depends on training. It depends on continuity. If that continuity is broken by conflict, environmental change, migration, or economic decline, technical traditions can fade. History contains many examples of skills that became rare or vanished, only to be rediscovered later. A forgotten technological chapter does not require a hidden global civilization. It could be local, it could be intermittent. It could rise in one region during a period of stability and fade in another period of disruption. Human technological history may not be strictly linear. Advanced phases could have risen and fallen long before recorded time, especially if advance is defined not by modern electronics, but by practical mechanical solutions to engineering problems. According to researchers who study early economies, innovation often grows where surplus exists: surplus food, surplus labor, surplus time to specialize. In such conditions, craftspeople can spend years refining a technique. Small improvements accumulate: a better guide frame, a more effective abrasive mixture, a more durable edge, a more reliable measuring method. None of this needs to look like a sudden revolution, but the results can be stonework that seems unexpectedly precise. Some engineers emphasize that precision does not always imply modern machinery. It can imply strong metrology. A society that measures straightness, right angles, and flatness can produce consistent results with relatively simple tools. Strings define lines. Plumb bobs define vertical. Water levels define horizontal. Straight edges can be created by comparing surfaces. Geometry can generate right angles. Once measurement becomes reliable, craftsmanship becomes repeatable. And still, the marks remain: the deep round holes, the straight cuts, the smooth planes, the repeated grooves. They sit at the intersection of archaeology and engineering, where interpretation depends on both cultural context and physical analysis.